Okay, this is podcast 2.2, and we're going to talk about how you can find the protons, neutrons, and electrons within an atom. So an atom is the smallest piece of matter that still retains properties of that element. If you think of maybe a gold ring is shiny, you can think of the color, you can think of the density. It is still going to have all those properties if we can break it down to just a single atom of gold. And then an atom is so tiny. If you think about the world's population is 7.2 billion, roughly, the atoms in a penny, there are this many atoms in a penny. So we're talking about things that are really, really small, and there are a lot of them because they make up everything we see around us. And to give you a better idea of how small an atom is, here is a quick video.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? That's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class, where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it's empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
All right, so you are going to use the periodic table to figure out how many protons, neutrons, and electrons there are. The periodic table is ordered by atomic numbers, and atomic numbers are protons. So the atomic number is the whole number that's in the box. Then you have the symbol, you have the name, and then the decimal number that's in there is the atomic weight. Sometimes it's referred to as the atomic mass. You can see it both ways. It means the same thing. All right, so important things that you need to know then about that. It says protons are the same as the atomic number, and we know that's true. If you change the number of protons in an atom, you change the identity of the atom. So every hydrogen atom has only 1 proton. Neutrons, how you find those are you take the mass number, and the mass number is that atomic weight. So if you look on your periodic table at carbon, carbon is listed around 12.01. That's the decimal. When you're trying to find the mass number is 12. You want to round to the nearest whole number. So you take that atomic weight and you round it. So neutrons are going to be the mass number minus the atomic number, because what we know is that the mass number is equal to your protons plus your neutrons, because those are the 2 subatomic particles that make up the entire mass of the atom. So we have protons are the atomic number, neutrons you have to do some subtraction for. Electrons are going to be the same as the protons for right now, because we're going to be talking about neutral atoms. If you remember, electrons have a negative charge, protons have a positive charge. Right now we want an overall charge of 0 on our atoms, so electrons and protons have to be the same. All right, and we have a little practice table. Okay, and we have a little table to practice here. So using your periodic table, if you go and find boron, boron is in the 2nd row, you're going to see that its symbol is B. Its atomic number is the whole number, which is 5. So since its atomic number is 5, the protons are 5, and the electrons have to be 5. We need to do some subtraction to find the neutrons. So I'm going to fill in these 2 areas first, and then I'll come back to do the subtraction. The atomic weight is around 10.81. Now, yours could look a little different. It just depends on the periodic table that you're using, but it should be around there, which means your mass number is going to be 11. And then to find the neutrons, 11 minus 5 is 6. So I want you to try the rest of these first before you watch me go through the answers. All right, Ca, if you look it up, is calcium. And if we find calcium, it has an atomic number of 20, which means there are 20 protons, 20 electrons. I'm going to go over here. For the mass number would be 40, because the atomic weight is around 40.08. So if we do the subtraction, 40 minus 20 is 20 neutrons. All right, we need atomic number 29. So if we go look, we're going to find copper. Copper is Cu. Some of these symbols do not match up with the names because they have names that were given in Latin or a different language. So that's why copper is Cu, maybe not Co or Cp like you would expect. All right, protons for copper would have to be 29 because the atomic number is 29, which means your electrons are 29. And then you have a mass number of, we're going to round that up to 64 because this is 63.55. So that will round that up to 64. Then to get the neutrons, we do a little subtraction. All right, 64 minus 29 is 35. All right, 79 protons. What that tells me is that my atomic number is 79 and I have 79 electrons. So if I go and find element 79, it is gold. Gold is Au. Another one of the weird ones. And then if we look at gold, its atomic mass is 196.97, which will round that up to 197. And then if we do the subtraction, we're going to get 118. Okay, in this one they're telling me the electrons are 80, and we said that right for now the electrons and protons are going to be equal, and that makes my atomic number 80. If we look for element 80, it's right next to gold, which is mercury. Mercury is Hg. So if mercury, Hg, atomic number 80, if we fill in the rest of this information, this is 200.59, which will round this up to 201. And then if we do the subtraction, 201 minus 80 is 121. My last one here is a mass number of 133. So you're going to go through and you're going to look at atomic weights and you're going to find the one that's the closest to 133. And that is going to be cesium. So cesium has an atomic weight of 132.90. And if I look at the rest, cesium is element 55. So 55 protons, 55 electrons. Cesium. And then if I do the subtraction, 133 minus 55 is 78. Make sure you can do these. They're really, really important. And the last thing we're going to talk about is standard symbol notation. So sometimes you're going to see the chemical symbol with extra numbers around it and you need to know what those are. So I need you to make sure that you copy this thing down. It is always going to hold true. If you see a number in the upper left-hand corner of the symbol before the symbol, it is the mass number. Under that is the atomic number. The charge will go into the upper right, and then how many of them is the subscript down below in the lower left, or I mean in the lower right. So examples of how you can do these. If you find sodium on your periodic table, it's Na. And if I want to fill in some information, I'm just going to focus on these two right here because we haven't talked about ions yet. So sodium, if I find its mass number, its atomic weight is 22.99. So mass number is going to be 23. And then if I want to know the atomic number, it's 11, and I would put it down like that. Carbon. If you find carbon is 12.011 for its atomic weight, which would make its mass number 12, and then its atomic number is 6. So make sure you're also familiar with these symbols and these numbers when you see them so you know what they mean. Okay, and that's the end of podcast 2.2. Make sure that you wrote down the symbol notation and that you know all the different rules for finding the subatomic particles.